So let me talk about another one, about the distance problem. And I'll spend more time on interaction of calculus and geometry and physics on that problem. It's going to be sort of similar to what we have here. But the reason I want to spend more time on that problem is that we will use that problem later, again, in a very unexpected and different setting. So I'm looking at the problem of distance from a point in 3 space to a plane. Now the setup, well, there are two possible setups. One setup is in your problem, both in the file and in WebAssign, saying that the plane is given by the equation. So in that setup, you just start with this point P. P is given, take a point on a plane. That point has unknown coordinates x, y, z, and you want to find such a point that the distance is minimal. And then you make that distance. The distance is going to be a function of 3 variables. And then there is a limitation of this point by the equation of a plane. And you don't treat, therefore, all 3 as independent variables. You say that from that equation you can solve for one of them. Say z equals something in terms of x and y, substitute, and get a function of 2 independent variables x and y. Proceed with minimization. So that process is straightforward, very similar to the, well, to the previous problem. I would rather focus on a different setup when a plane is given not by equation, but rather by 3 points. So what if you have Q, R, and S? 3 points on the plane. So we agreed some time ago that 3 points determine the plane in 3 space, right? So how do they actually determine the plane precisely? Well, how do we figure out a point on the plane, having those 3 only? Well, we say that that point can be, choose it there, can be obtained using these vectors. So you start with this vector u from q to r and the vector v from q to s. And you can possibly get from this point on a plane, from the point q, if you follow the vector u for some time, and then you follow the vector v for some other time. Or alternatively, you can follow the vector v for some time, and then follow u. And what you have to imagine here is parallelogram, which it is not, but it's supposed to be. Okay, so a point now is a result of beginning at q, and then following a vector u for some time t, and then following the vector v for some time s, and finally arriving at q. And you cannot possibly arrive at any point outside of that plane using that procedure. So that procedure determines the whole plane and the plane only. And then if we want the distance from P to that point, well, we just make that distance. Look at this vector. Let's call it W. So the distance is going to be magnitude of that W, which is the magnitude of the endpoint minus the beginning. So Q plus U times T plus V times S minus P. Then this distance becomes a function of two variables. So we can treat it as a function of two independent variables, T and S. And that's what we want to minimize. And again, in this setup, we are ready for calculus. Saying that the derivative of that function needs to be 0 at the point where minimum is achieved. And that means the system holds partial of f with respect to s is 0, partial of f with respect to t is 0. And then we can, computationally of course, we can go and set up these equations, solve the system, find the point. There is no problem. What I would like to explore is the understanding of that. What does that mean geometrically? So again, what is the partial of f with respect to s? Well, we are facing exactly the same problem we did a minute ago. So you have to differentiate with respect to s the magnitude of a vector, which is the vector itself dot producted with its derivative over its magnitude. And then the partial with respect to s is going to be exactly that v, because everything else doesn't depend on this. So the partial with respect to s is w dot product v over magnitude of w, and the partial with respect to t is in a similar way. And that is w dot u over magnitude of w. So that system of two partials being 0 amounts to saying that w dot v is 0 and w dot u is 0, which means that w is perpendicular to v and also w is perpendicular to u. So again, those two conditions say very precise things geometrically. First condition says that this vector must be perpendicular to v. The second says it must be perpendicular to u. And the condition itself says that those two should happen simultaneously.